Okay, so welcome back, everyone. Here's an outline. We're going to review the infinite well or particle in a box, talk about the finite well or finite square well, and then the finite a barrier, a potential barrier, and then the quantum harmonic oscillator. Well, this one we'll finish next time. We'll have an introduction to it, but we'll finish next time. So the infinite well, just to recap, for the infinite well we had the following. Infinite we had the potential. Potential is 0 for x between 0 and f, and it is infinite otherwise. Or, yeah, it is infinite otherwise. Now, remember the Schrodinger equation, it says this. The time independent Schrodinger equation, it says minus second derivative minus h bar squared over 2m, second derivative psi with respect to x, plus the potential times psi is equal to E times psi. Now, outside here, for outside of the well, meaning when x is less than 0 or x is greater than L, the potential is infinite. Now the wave function must be finite. In fact, it must go to 0 when x goes to infinity. But if the potential is infinite, the only way to make left and right sides equal is for the wave function itself to be 0. So outside of the well, so the potential psi will equal to 0 for x less than 0 and x greater than L. So it is, the wave function is just 0 outside. Okay. How about inside the well? Now inside the well, we'll write the Schrodinger equation again, and we will solve it. Inside the well, though, u is equal to 0 inside. So this term will drop, and we'll just have the following. Minus h bar squared over 2m, second derivative psi with respect to x is equal to E times psi. Okay. This one here. And we'll simplify this. We get the second derivative of psi with respect to x is equal to minus 2me square root over h bar times psi, which is equal to, actually no, there is no square root, right? I'm kind of ahead of myself. Over h bar squared is equal to minus k squared times psi, where k is equal to twice me square root over h bar. Okay. Any questions on this? This is what we did last time. I just want to go over it now. So this is just this is what k is. Okay. All right. Then we asked, what's the solution to this? Where the second derivative of the function is proportional to the function itself with a minus sign. It was sines and cosines, right? The solution to this was psi of x equals to a times the sine of kx plus b times the cosine of kx. Who remembers what was the next thing we did to this?
We showed that b can only be 0.
Can only be 0 by invoking that psi has to be continuous, right? So if psi is continuous, it needs to be continuous at the endpoints, at the boundaries. So, for example, we know psi at 0 will have, if we plug in x equal to 0, this term will just become 0 and we'll just get b, right? Because cosine of 0 is 1, so just get b. But we know outside of the well, the wave function is just 0. So when x is just less than 0, the wave function is 0. Greater than 0, the wave function is b. So for them to match, b needs to be 0. So the wave function needs to be, in order for them to match, I need to have this. Therefore, psi of x becomes just a times the sine of k times x. Okay. The next condition was psi at L, at the other boundary. Well, at L, we will have a times the sine of k times L. And we know to the right of L, the wave function is 0. To the right of L, the wave function is 0. So this needs to also equal to 0. To the left of L, for left and right need to be equal to each other for it to be continuous. So this condition must be met. There are two ways to meet this. Either the sine is 0 or a is 0. A cannot be 0 because if a is 0, then we're saying the wave function itself is 0 everywhere. And that's mathematically okay, but physically it's not. If the wave function is 0 everywhere, it means the probability of finding the particle anywhere is 0, because 0 squared is 0. And so that's not a physical solution. We want this then to be 0. For this to be 0, we need k times L to equal to a multiple of pi. Okay, a multiple of pi. Now n equal to 0 needs to be excluded, because again, if n is 0, this will make the entire wave function to be 0, and that's not a physical wave function. So we get then k will equal to n times pi divided by L, where n is 1, 2, and so on. Knowing k, we can determine the energy now. Now the energies, to determine, you just square both sides. We know that you have this. The energy will just be h bar squared, k squared divided by 2n. And so this means the energy will equal to n squared, h bar squared, pi squared divided by 2n, and then l squared. Okay. Again, this is review from last time. I hope it makes a little more sense, or maybe it already made sense last time. So I hope this helps more. Okay. Now h bar is h over 2 pi, so we can replace h bar by h over 2 pi and write this as the pi h pi squared h squared over 8 m times l squared. Okay, that's the energy. All right. Now, then we said, okay, the wave function needs to be normalized. Yeah,
Did the pi's cancel out?
the pi cancels out. Yeah, so no more pi, right? Here? Yeah.
I think n squared.
And n squared. Yeah, a lot of mistakes. Thank you. Appreciate it. Okay, yes. Anything else? Okay. Now, the wave function, we said it must be normalized. Normalized means this. Needs to equal to 1. Now, the only relevant interval is from minus 0 to L. You get a squared sine squared of k times x dx. Okay. The reason from 0 to L, because what is the wave function when x is less than L? It's 0. What's the wave function when x is greater than L? It's again 0. So the only interval that really matters is from 0 to L, equals to 1. And we integrated this by doing some trig substitutions, or trig identities, and we found that A was equal to 2 divided by L under the square root, and therefore psi n, I put subscript n of x is equal to 2 over L square root sine of n pi x divided by L. This is sine n. This is what we need, or what's useful for us. Sure. I also mentioned, for completeness, if you want this one, the time-dependent wave function, psi n would be psi n of x times e to the minus I e n times t over h bar, and that becomes 2 over L sine of n pi x over L times e to the minus I e n times t over h bar. That was psi n.
We also did this, right?
And these are the energy, the wave functions for each n, the time dependent. Now, in general, you can represent any other wave function in terms of these by just, because the sum of two solutions is also a solution. Okay, the sum of two solutions to the Schrodinger equation is also a solution. So a linear combination of these is still a solution. So in general, psi and no, just psi of x and t, any wave function here will equal to the sum from n equal to 1 to infinity of some constants Cn, that those you have to determine them in order to find the wave function. 2 over L and then sine of n pi x over L, and then e to the minus I e n t over h bar. Okay. This is just for completeness. We will not work with this at all. This is what we do. This is the one. Have you seen these? You have calculated these coefficients in differential equations, right? Yeah. So I will leave that for the math class, not for here. So we'll just work with this. Let's do a quick example here. Find the first two energy levels for an electron confined to a one-dimensional well. And the width of the well is 5 times 10 to the minus 10. So an electron, example. An electron in infinite well with L equal to 0.5 nanometers. Okay, find E1 and E2, the first two energy levels. Okay? Find the first two energy levels, and well, the energies are over there. Let me write them. En is equal to n squared h squared over 8 ml squared. Now, often it's convenient to work with this one instead of the one with the h bar. The one with the h bar involves a pi, so you have to plug in more stuff. So I like this one for calculation. So I get, so we will just find E1. So E1, it means n is 1. So we just have h squared over 8 m times L squared, and that is 6.626 times 10 to the minus 34 joules per seconds. squared over 8, mass of the electron. And then the width of the well. This is half a nanometer, that's 5 times 10 to the minus 10 meters, 10 meters, but we have to square.
And so we get the energy. You will get a number in joules, but I want EVs are more convenient to work with, and it turns out to be 1.5 EVs.
Okay, so this one is just gonna be 1.5 electron volts.
Again, when you plug in these numbers, you'll get a tiny number, that'll be in joules, but you have to change it to EVs, so you get EVs.
And feel free to check it. Now, knowing N1, we can easily find N2. Notice, En, let me write it here, En, it's N squared E1, right? Because this part is E1. So E2 will be how many times E1?
4 times.
Yeah, 4 times. 4 times E1 is going to be approximately 6 EVs. Volts. Any questions on this one? No? Let me restart the next one with the finite well.